Now, I've been talking about lines and vectors, and I want to continue that discussion a bit here. And in particular, I want to talk about the dot product between two vectors. Now, just as a quick review, remember that right now I'm talking about three-dimensional space, and that a line in three-dimensional space um, has infinite length. It goes infinity in both directions, and it has slope, and it goes through a particular point. And so a line has, what characterizes a line are its slope and a point that it must pass through. A vector, on the other hand, has slope, but it's not infinite. It has a particular size, and it doesn't need to go through any particular point, and that we can imagine writing the same vector, drawing the same vector in just about any place in three-dimensional space. Usually we'll draw it beginning at the origin, or we might draw it beginning at the end of another vector. So the vectors and lines pass through a particular point and have slope. Vectors have a particular length and a particular slope, but don't pass through a particular point. So here I have two vectors. X is equal to AI plus BJ plus CK. I, J, and K with the little hats on them are the unit vectors in the X, Y, and Z direction. Y vector is CI plus DJ plus EK, and it's just a coincidence that I have the same number, the same symbol here and here. They don't need to be the same, they can be different. Now in class I define the dot product between these two vectors. I use this notation. I say x dot y. Now x dot y also equals y dot x. Doesn't make any difference what order you do it in. X dot y I write as follows. Here I have my x vector dot my y vector, and I compute a times c plus b times d plus c times e, and I just add those up, those products. So I multiply the I components of the two vectors, add that to the product of the j components of the two vectors, and add that to the product of the k components of the two vectors. So this is how I've defined my dot product in class. Now, something I also mentioned, but I didn't prove it, and I'm not going to prove it here in this video, is that another way we can write the dot product between two vectors is something like this, where we can have our vectors x and y as I've drawn them here, and I can say the dot product between x and y is equal to the length of x vector, or as I've written it, as a magnitude, or x with an absolute value sign around it. I might put an arrow above here, times the length of the y vector, okay, times the cosine theta, where theta is the angle between the two vectors. Now, you may recall that in three-dimensional space, if I have two intersecting lines, okay, and they're not the same line, they're two different lines and they intersect at a point, that those two lines must lie in a plane, and they lie in only one plane. Same thing with vectors, as if I give you any two vectors in three-dimensional space, those two vectors will define a plane. There is only one plane that contains both of those vectors. There aren't two planes that contain both of those vectors, and there will always be one that will do it. So if we draw those two vectors in a plane and we look at the angle that those two vectors make, if we have them both starting at the same point right here, then that angle's theta. So another way of writing dot product is x dot y is equal magnitude of x times magnitude of y times cosine theta. Now let me look at a particular example here. Let me pull this up and let's look at two vectors. Okay, right here. Say, one thing I also want you to note here is that we, here I am. It took me a while to find the right place here. There we go, right here. Okay, so let's look. here I have my vectors x and y, and I'm going to use as my example, I'm going to say that y vector is equal to 1 times I plus 2 times j plus 3 times k, and x vector is equal to 1 times I minus 2 times j plus 2 times k. So this is an example now. And I compute the length or the magnitude of y vector, and by the three-dimensional Pythagorean theorem, this is just equal to the square root of the sum of the squares of the coefficients of I, j, and k. So that's square root of 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9. So I have 1 plus 4 plus 9, that's 14. So I'm looking at the square root of 14 is the length or the magnitude of y vector. Now I look at x vector, and I want to compute the magnitude of x vector. Here that's 1 squared plus negative 2 squared plus 2 squared. 1 squared plus negative 2 squared plus 2 squared. 1 squared is 1, negative 2 squared is 4, and 2 squared is 4. So I have 1 plus 4 plus 4, that's 9. Want to do the square root of 9, and that's 3. Okay, so I have that the magnitude of x is 3, and the magnitude of y is the square root of 14. Now suppose that I want to compute the dot product between the two vectors x and y. So I do that by doing 1 times 1 plus 2 times negative 2, 2 times negative 2, plus 3 times 2, 3 times 2. So I add these up. That's 1 minus 4, 2 times negative 2 is minus 4, plus 3 times 2 is 6. So 1 minus 4 plus 6, that's also 3. Now it's just purely a coincidence that the dot product of the vectors is 3 and the magnitude of x is 3. Okay, that type of thing isn't generally going to happen. Okay, now remember, I also said the dot product can be written as the magnitude of x times the magnitude of y times the cosine of the angle between the two vectors. Well, I plug in what I've already computed for the dot product, that's 3. So 3 must be magnitude of x times magnitude of y, which is square root of 14 times 3, square root of 14 times 3, times the cosine of the angle between the two vectors. Now the 3's here cancel. Okay, that 3 cancels with this 3. So I end up with 1 equal to the square root of 14 times the cosine of the angle between the two vectors. Or, in particular, what I have is that cosine of theta is equal to 1 over the square root of 14. Now, you can use the inverse cosine function on your calculator, or sometimes called the arc cosine, and you can find out what theta should equal. So inverse cosine of 1 over the square root of 14. You work that out. Let me pull out my calculator and figure it out right here while I'm doing this video. And I put in 14 square root, and then arc cosine. Let me try that again. I got an entry error. 14, enter, square root, 1 over 14. Arc cosine, that's 74.5 degrees. Now, there are two angles that give me the cosine of 1 over the square root of 14. The two angles are 74.5 degrees and negative 74.5 degrees. So technically speaking, I can put a plus or minus there. But in general, here what I have is that this angle, if I'm just looking at the absolute value of the angle between x and y for this example, is 74.5 degrees. Now let's go on. Let's keep looking at this example here. Now suppose that in particular, one of my vectors was a unit vector. Okay. Now a unit vector is any vector that has length 1. And in fact, we can get a unit vector that goes in the same direction of any vector by doing this. We can take, suppose I can take my x vector from the last example. I can divide x vector by the magnitude of the x vector, and that gives me a unit vector. And I always write my unit vectors with little hats on them. Okay, so what that means, for instance, if I look at that other example, my x vector was 1, -1, -2, 2. So I can compute the unit vector. Let me do it right here. I can say x unit vector is equal to 1 over, remember the magnitude of x was square root of 3, 1 over the square root of 3 times I minus 2 over the square root of 3 times I plus 2 over the square root of 3. Now this is j, not I here. J hat, I hat, plus 2 over the square root of 3 times k hat. So this would be the unit vector that points in the same direction as this x vector. So with that now, suppose that x were a unit vector to begin with. If that were the case, I come down here, I say, okay, now if my x vector, magnitude of my x vector equals 1, any vector of length 1 is a unit vector, and in that case, x dot y, which would equal magnitude of x times magnitude of y times cosine of theta, the magnitude of x is 1, so this just becomes 1 right here. This is 1. So what I have is that x dot y is equal to magnitude of y times cosine of theta. So let's think about what the implication is. Suppose I draw a triangle, and the hypotenuse of my triangle is the y vector, and it has length magnitude of y. I make this a right triangle like this. So in particular, I'm looking at what is the length of this side of this right triangle if the length of this side is magnitude of y. Well, if this angle's theta, the length of this side right here is just magnitude of y cosine theta. So this side right here is magnitude of y cosine theta. So you can think of it something like this. I do the dot product between x vector and y vector, but x vector has length 1. And I do the dot product, and so here's my x vector. I've drawn it in red to emphasize here that it's a unit vector. So here's my x vector of length 1. Here's my y vector. The dot product between x and y is equal to magnitude of y cosine theta. So that tells me what the length of this line is right here. So you can think of it, if the sun were out here casting a shadow of the y vector onto the x vector, that's what we call it, a projection. And we say the projection of the y vector onto the x direction here, this is a unit vector, the projection of the y vector onto the x direction is just magnitude of y cosine theta. Okay, so when we talk about doing a projection of one vector onto another, we do it by doing dot products like this. So we get the projection in general by doing something like x dot y. So the projection of the y vector onto the x vector is x dot y divided by magnitude of x. The projection of the x vector onto the y vector is x dot y, same dot product here, x dot y, and there we divide it by magnitude of y. So this is how we do projections, okay, in three-dimensional coordinate geometry. So project vector y onto the x direction yields a length of magnitude of y cosine theta, which is x dot y divided by magnitude of x. Now I have a three-dimensional drawing example. So let's look at that and see what we get. Let me pull this down. So here's my three-dimensional drawing example. Okay, now here I have the blue vector. okay, right in here. And the blue vector is it's ABC. It's 1 times I vector. Look up here on the top, right in here. 1 times I plus 2 times j plus 3 times k. So that was a vector from previous example. And I have it drawn here, my three-dimensional coordinate axis. That's the blue vector. Okay. Now let me draw my other vector here, the red vector, which is 1, negative 2, 2, right there, just like that. Okay, so again, that's a vector from the last example. Now remember I told you that these two vectors form a plane in 3 dimensions. So you look at them right here and you say, yes, I can see that. I can see where the blue and red vectors actually define a plane in 3 dimensions. There's only one plane that goes through both vectors. Okay, so you can see that here. Then what I want to do is, using that dot product, I want to do that projection onto the, let's say, of the blue vector onto the red vector. So I use the dot product to do that. And what I get is this white segment right in here. So this, I'm claiming right here, this white here is a projection of the blue vector down onto the red vector. And also, I'm claiming that if we drew a line from the tip of the blue vector down to the tip of this white vector there, that would be 90-degree angle. And I draw that right here. Okay? And that's exactly, I think you can see that that's what it is there. That's a 90-degree angle. So these are the same two vectors from the last example. I've done the projection of the y vector onto the x vector. I think that's the way we went. And it gives me this length here. Okay, this is the projection. This is a right triangle, as you can see. And this angle right in here between the blue and the red, that angle right there, I'm saying was 74.5 degrees. And you look at it, and that looks like that's just about right to me. Okay, so that's an example of how this all works. And until next time.